Okay, I think we're about ready to go here. I had to reboot my computer twice to make it work. Um, let's see. All right, so where were we? So we're talking about hill climbing as a new type of search for us, and we're almost done talking about hill climbing because at the end of the day, there's a couple things you need to know. One of which is this idea of, hey, look at the neighbors and evaluate them and go to the best one. Maybe with some randomness thrown in, right? And then there's this idea here, which is that, okay, but if your variables are continuous, computer science continuous, floating points, okay, what you're going to do instead is you're going to look at derivatives, partial derivatives of the cost function, okay? And you're going to get that derivative and you're going to multiply it by a small constant and add that to each parameter. And as we saw in this example right here, it does the right thing, right? Here, negative slope, it's going to climb. If you started here, positive slope, it's going to climb here. Okay, so it looks kosher, right? Now, the thing that might not be, which is a multivariable calculus topic, so unless you had a full course on that, you won't, it'd be hard for me to prove it to you, right? To really tell you in a convincing way. But in fact, when you are in multiple dimensions and you update each parameter using this equation, if you think about where that's actually going to take you, by the way, you don't do it one at a time. You do the derivatives at one time, and then you step in a particular direction. Well, what direction is that? Well, it's a direction that is composed of, basically a vector, which these partial derivatives are the components of that vector. Okay? Now that vector has a name, that's the gradient. And it has the property, a provable property in a math course, that direction is the direction straight uphill from wherever you are. Okay? So not only does it take you in the right direction, so okay, maybe it's kind of reasonable, and it's taking you in the best possible direction. Now, again, it's calculus, right? So we know about derivatives. Yeah, that gives you the exact the slope that's of the tangent line to the curve at that point. And as soon as you start to get even a little bit away from the point, your quality starts to go down. And after you've moved any finite distance away from the point, all bets are off because your function could be horrible, right? Which was a positive slope. Where you measured it becomes a negative one because it's a jaggy curve. Okay? That's the way it is. And that's the reason why these learning rates, it's safest to let them be small, but then your algorithm's super slow. You're going to take tiny, 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 tiny steps. Okay? I'll be talking about some of those issues today. Okay, so let's go. Right. So this is what we do when we have multiple variables around. Excellent. Okay. Yeah, here we go. Problems. Okay, let's make a list. Okay. There's the old local maximum problem, which I think we'd be beaten to death at this point. We understand that just climbing from wherever you start does not take you to the top of the tallest hill. It takes you to the top of the hill you're on. Okay. So that's the first issue. Now the second one is that, hey, this quality function, again, unless you got to put on your worst case hat like we had for systematic learning, this has to be a continuous function, but aside from that, it could be as badly behaved as nature could provide us. Nature plus the hand of man in making bad choices in parameterizing whatever data they want to process. So it can get really bad. Okay, what kinds of things could you see that would be really unfavorable to this particular algorithm? One would be that in the terrain, right? This is my cost function. We want to climb, well, no, value goodness function, right? Okay, Q, quality function. We want to climb uphill for the moment, right? And so that's the shape that we want to climb. And so what if we have a plateau in that shape? Right? So a plateau means it's not a plateaus are all plateaus aren't completely flat on top. If it's completely flat on top, you're dead. Derivatives will be zero. Okay, but if it's not completely flat, but it's pretty flat, then what happens? Your gradients get close to zero, and the algorithm's going to make very slow progress toward the peak. Okay. Now, if you add into that the fact that in practice, when you actually use these things, your gradients are liable to have noise in them. Okay, that means now you've got a little bitty signal, which is the actual gradient pointing you up. All the components are really, really tiny, plus now some noise, which might be much bigger. So in fact, when you're trying to move to the right here, what you may end up doing is a drunkard's walk. When I say random walk in there, that's actually a term of art from mathematics. I mean, it's a drunkard's walk. Take a random direction and take a step. Take a random direction and take a step. You end up doing something that looks like you're not making any progress at all. Maybe only after you look at it for a very long time, you realize, you know what? It's actually drifting a little toward the right? Becomes hard to see that you're even making progress. And in practice, even if you're patient, you're going to have to wait. You're going to have to spend compute cycles. None of those things are good. Okay, the next thing that can happen is that you can have a very narrow, sharp ridge. Okay, let's think about what happens when you have a very narrow, sharp ridge. So if I have a narrow ridge, maybe with the peak in the middle over here, and I'm over here on the side, does the steepest way uphill, the gradient, is it going to point me directly toward the solution? Where is it going to point me? Right? I failed miserably with a capital type diagram over here. I think you do it this time. This is a different issue. Narrow ridge, right? This is the narrow ridge. Okay? And we're over here. Which is the steepest way uphill? This is where we want to go. Is the steepest way uphill going to point me in that direction? No, it does not. Where is it going to point me? It tells you to go right up to the ridge line. Right? That's where it tells you to go. It tells you to go like this direction, almost perpendicular to where you actually want to go. Okay. See? And what you can end up with, depending on your eta size, is you can end up taking a step that bounces you to the other side of the ridge, which tells you then to go back to toward the peak of the ridge, and you end up doing this. Again, if you are patient and do the right filtering on that data, you'll realize, oh, it actually is drifting in a consistent direction, but it's slow. Okay? So similar problem to a plateau, different topography, but also ugliness with now oscillation added into the mix. Okay, now another thing you can have is that you can actually get instability. Okay, where the parameters actually blow up. They become not a number. They'll get bigger, 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 become not a number. Okay, this can happen because even though the math is all correct, okay, derivatives are only valid close to where they're taken. So if your eta ends up being too big for how terrible your topography is, how steep, right? So like what's the steepest, you might expect in real life, these topographies can be very arbitrarily steep. Okay, so even with what you thought was a very modest eta, the learning rate, multiplying that now very large gradient, that ends up being a large step. Okay, and because it's a large step, so we can end up with the story is kind of similar to here, but we're taking it from the side here, right? And I'm being told, I'm over here, I'm being told to step in this direction, but let's say my eta is too big. Right? Eta is going to the derivative is what it is. With the eta tuned large, I could be taking a step of any possible size. Right? And if it's too large, I can end up doing this. I can end up overstepping. Not only overstepping past where I would like to stop, but I could end up further away from that point than I started after one step. Got it? Further away. The whole point of the algorithm is to get you closer, but you end up further away. Not only that, but if we assume that this is just a parabola and it has the same characteristics down forever, when I step back in the other direction, what do you think I'm going to do? I'm going to overstep even worse. And then worse. And in very few steps, you're seeing that you're getting infinity for your parameters, or not a number, or some useless value. Okay? That's instability. Any question about any of these? Okay, so these are important. You'll hopefully get this reinforced to you when you start in on the next lab on Friday. But make sure you understand these things. They're squishy, they're qualitative things, but they're important. It's qualitative because we don't have good mathematical theory that's valuable to add to this. So make sure you know this such as it is, because it's the difference between being able to actually train a neural net properly and just failing constantly and not knowing why. All right. Yeah, so just so you know, I used to talk a little bit about different approaches to add noise in a continuous framework, but it's really not very common that we add noise. We're going to have noise thrust upon us, as you're going to see very shortly. And that noise, sometimes, again, it's just noise. It can have a good effect. Yeah, right. Remember, why were we talking about adding noise? Because of this local maximum problem. We were hoping that it would bounce us from a little hill, maybe onto a bigger hill, and we'll get a better result. Okay. And so that's what, in fact, does happen when noise shows up in our systems. Okay, but I'm not going to talk about intentionally adding noise, even though it's a logical possibility. So I'll leave that on the side. Okay, and that's pretty much it, except I have some big picture questions here to see how well you're digesting that. So let's have a little bit of discussion here. Okay, first question. You all had a calc class. You probably were asked to find maxima, extrema of a function. Yes, that's like a normal thing a calc class asks you, right? So, like, why are we doing this at all? Since in calc class, they tell you how to, I mean, you don't mess around with an algorithm or any of that stuff. You just like, you go through a computation and it tells you the extremum is here and you're done. So why don't we do that?
I assume the big functions you're going to run into with these larger systems are going to be significantly more complicated than like the two little loops that I was working on in calculus time.
Yeah.
So probably finding mathematically the actual local minima is significantly more computationally complex than just stepping around until you find.
Yeah, well, yes, that's fair to say. Yeah, so the difference is when you do it in math class, they only give you problems that have a solution. Okay. And if you recall, what do you do to find an extremum? You take a derivative, you set it to 0, that's where the extreme points are, and then you solve that equation. Okay, are all equations I could write with blah, 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 blah equals 0, are they all solvable in closed form? They all have an answer? They don't. Most of them do not. In math class, they all do because they're pre-filtered for you. Okay, but in real life, they mostly do not. Okay, so what we'd be doing is incremental kinds of, we'd be going back to this kind of approach here to try to solve that equation, blah, blah, blah equals 0. So it's not a win. So in fact, we are incorporating everything we can from calculus, and it's just that it just doesn't solve problems that are harder than the textbook problems very nicely. Okay, let's see. Let's see. I think some answers here. Let's see if there's anything more. Yeah. So here's an example okay, if just so I think you all kind of nodded through that, but still, right? If you take an example like this, right? If this is a function, this is not as complicated as things you will see in any kind of a neural network or any kind of a applied engineering setting, as a general rule. If we take a derivative to that and set it equal to 0, what are we going to get? We're going to get some constant times x plus negative sign equals 0. That doesn't look that bad. Does that have a closed form solution? It does not. It does not. So something as simple as that cannot have a closed form solution. Polynomials, if it's it's blah, 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 x squared plus blah, 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 x plus blah, blah, blah equals 0, we all know. Quadratic formula, right? You know how to find a 0 to that. What if it's third order? Third order polynomial. Ax squared plus ax to the cube plus bx squared, okay, equals 0. That have a closed form solution?
Yes.
I don't think it depends. I think the answer is yes. It used to be taught. before computers. Because the formula is really awful. If you thought quadratic formula was complicated, look at the formula for third order polynomials. How about a fourth order polynomial? I'm told you can do the same thing with fourth order. I've never actually seen the solution. It's probably really awful. What about a fifth order polynomial? Okay. Now it's mathematically proven there is no general solution for fifth order and above polynomials. So even polynomials can't be solved with this kind of an approach. Only easy polynomials can be solved. Okay. All right. Point made, I hope. All right. Discrete and continuous. That's a pretty vague question. So let's see what I have in mind here. Discrete versus continuous hill climbing. Right. Hopefully you already got all of this out, right? Discrete hill climbing, we can look at all the neighbors. Continuous, we have to assume the function's smooth, and therefore the derivative, let's just shortcut that process of considering a whole spectrum of possibilities, and it just says go here, and that should be the right answer. Okay, again, to the limits of the fact that we're abusing the calculus, right? That the derivative is really only true in an infinitesimal area around where we evaluated it, and in fact, we want to take finite steps. That's not finite step is not an infinitesimal step. So we're always abusing the calculus, but except for that, we should be good. Okay. Does that make sense to you guys? Questions? Good? Okay. And last, to defeat local maxima, when is it better to add noise versus simply doing a random restart like we talked about? Okay. It's possible to imagine at least some extreme examples here where I think one or the other is obvious. So if you consider a function like the one in the little web demo I had, which is basically one hill, but it's got a bunch of bumps on it, right? And you saw in that example, wherever you come down, unless you come down really, really, really close to the peak, you're going to just climb one of those little bumps, right? Okay. In a case like that, noise might be adding noise to the problem might be a win, right? It might just because all you need to get bumped over is a tiny bit, and then you'll be on a better peak. And if you get noise bumps you again, you might get onto an even better peak, okay? Rather than just starting over and hoping for luck, okay? At the same time, you could imagine an extreme opposite kind of setting where you have peaks that are widely separated from one another, maybe with even zero derivatives in between, or there's no good way to move in between the peaks, and you would have no choice other than to do random restarts and just hope to get onto a better peak than what you had. Okay, that's it. That's hill climbing. It's really not that bad. All right, so unless there are questions, we'll move on. Let's apply hill climbing to its most important use case for us, which is neural networks. And right. All right, so let's get started. So this starts our whole machine learning unit, which could have other things. There are other things other than neural networks in machine learning. And in fact, I'm not even sure everyone considers LLMs to be absolutely a neural network. Anyone know? They could just as well be considered a neural network. But there are other things in machine learning that are worth knowing, but not in a 10-week course where we don't have much time. We're going to focus in on the main one that everybody's using, which is neural networks. But to start with, let's have some general discussion about this is the first time we're talking about having a machine learn anything. Okay, so let's just talk about that. Right. What does it mean? How is it possible? Then we'll talk about individual artificial neurons, putting them together into networks. We'll talk about reinforcement learning, and that's most of what we're going to do. We'll also talk about some generative AI, I hope, at the end. Now, some of these links here might be good for you. So this is a free book that's online on neural networks. So that's by Bengio. He's one of the which prize did Bengio get? I don't think he was on the team that got the Nobel for the for machine learning type stuff. I think he maybe there's this highest computer science prize, but I forget what it's called. I think he was one of the three that got the prize that time. I could be wrong. Anyway, very well-known guy. So pretty authoritative guy. Covers a lot of topics there. The book isn't super new, but if you want something that's readily accessible, free online, from someone who should know his stuff, might be okay. Other things, so I try to make my lectures such that you can all get what you need out of them, but some people have still found some stuff on YouTube to be particularly useful, and I've not vetted these myself, but I've heard it from students enough times that I believe it. So these are a couple YouTube channels that prior students for this course have found it useful. So have found useful. So your mileage may vary. Give it a shot if you want to hear things from a different voice than mine, which is a good idea for complicated topics. All right, so let's talk right from the get-go. So we want to talk about what learning means, and I'll include in learning adaptation because that really just means the same thing as far as I'm concerned. And it's all really kind of fuzzy. So it really does need some attempt at grappling with it. And I don't have a way to give you one nice, tight, authoritative definition any more than I did for AI. It's pretty loose. Okay, but minimally, it implies a change in behavior over time. All right, can we agree with that? If someone says a system's learning or it's adapting, but it doesn't change at all, that one's out. All right, I don't know how much other stuff I can throw out because I think you've got to have a pretty wide aperture here, but at least that's got to be out. Okay, so what we want to see, what we're expecting is, faced with a specific type of situation, your agent, your AI, behaves one way at first, and then, based on his experience or training or some kind of learning process, behaves differently later. That's what we're expecting when we talk about adaptation or learning. Okay, that's the minimum. Now, goes without saying that the change in behavior should be for the better. But for like realistic algorithms, there often is no guarantee that every change is going to be for the better. Yeah, but that's what, if it's a successful adaptation or learning, whether it's of a person or of a system, of a computer, some computer code, the changes in behavior better be in general for the better. Okay, so we could then put these things together and say, okay, we roughly define learning as an improvement in behavior in response to experience. I think that's fair. Discussion? Anyone offended by that definition? It's pretty open, but I think it's reasonable. I like it also because it focuses on what's important, which is the actual behavior of the system, which means its functionality. Okay, it's not focused on, it's got to have a neural net, or it's got to have some other cool GWiz CS technology. I really think that doesn't matter at all. At the end of the day, if I'm just going to be the user, I don't care how you implemented it. I care about the functionality. So if you're just doing it with ifs or case statements, and that's your AI, but it makes changes in behavior over time, and they're good changes that I want, and I don't care. I'll buy your product. Okay. You could be just changing some data structures, right? That could be the change over time. You could just be, you could actually be rewriting the program. You heard genetic programming? You heard about genetic algorithms the other day, right? It can design cool two-wheeled race cars, right? But genetic programming has been around forever, and that's using a similar approach to write programs. They use mutation and crossover to actually do programming. Yeah. I don't care if it works for the domain. I'm going to call it legit adaptation learning. Okay. And it's pretty clear if my definition is
Sorry,
Andy.
real quick.
Yeah, please.
For that purpose, then maladaptive stuff would not be considered,
Yeah.
when it happens that a system will adapt in a way that is maladaptive.
If it generally maladapts, right? Generally maladapts, then I won't want to call that legitimate adaptation learning, right? That's just degradation over time. That's what that is. It's a degrading system, right? If it occasionally maladapts, but actually it's good, right? Like think about the LLMs, right? They could do some, if you think about the worst case of what lies or hallucinations coming from an LLM might do to a system composed of humans and computers, that worst case is really, really, really bad. Okay? So if that was all it was doing,
we would not want such systems around. But the fact that it does generally good stuff, but occasionally does bad stuff, now it's not so clear whether we want to.
So then is it relative to the evaluated? Because, you know, we take the Army, for example, we, 10 years ago now had this Army line study where basically people were, you know, they have all these training demands and they have to meet them. So the point of the study was they learned to lie to meet them. They learned to just say like, oh yeah, hey, I got that done, etc. Well, relative to the evaluated behavior, they did improve, massive improvements, possible improvements.
Yeah.
However, I would say in terms of either training, it wasn't adaptive. So that would make the definition of learning then relative to the metric you're evaluating.
It certainly would. Yeah, and if you got a poor metric, yeah, you can have a system that looks good and is still bad. Yeah, I totally agree. All right. So again, so if it used to be a thing that, you know, a vendor of a system is going to come and say, oh, it learns or it adapts without a lot of additional description. And so that really begs for a comeback question of adapts and learns compared to what? I mean, what are you changing that other systems don't change? You know, and can you tell me something about how you know changes will be for the better? Again, even some of the best systems we have these days, there's no guarantee the change is going to be for the better. So I'm not asking a vendor for the moon. I'm just saying if he thinks I should buy his system, he should have something to tell me about how he's tested it, or, you know, tell me something to give me confidence that this is actually an adapting system and not a degrading system. Right?
That's just some life advice, kind of. All right. Now let's talk about systems that learn, whether they are people or whether they are machines, face a couple of, you know, really serious challenges. I mean, challenges that are serious enough that really it's amazing that they can be overcome at all from, you know, I think legitimate perspectives. And the first one of these problems is the problem of induction, right? So this is a known problem documented in you know, philosophy literature from the 19th century, right? And it was I think it was Hume or just Mill who saw it first. I think it was Hume. He was asking, he said, okay, when you roll one billiard ball, I think that was actually his example, was billiard balls, and you roll one billiard ball into another, you know, we know what's going to happen, right? Click, one maybe stops moving, the other one moves away. You've seen it a lot, okay? And he's saying, okay, you absolutely know that that's going to happen, right? How does a person actually know? Okay? Are you positive? Are you positive that the one ball can't roll through the other one? Right? And it's like, I don't believe that could happen. I've never seen it happen. But when you think about it, what we learn from experience is never completely authoritative. Because I rolled a billiard ball into another one, you know, 10 times, and it's never gone, well, the first ball's never gone through the second one, doesn't mean that it couldn't still happen. And rolling it one into another 1,000,000 times still doesn't guarantee that the strange output can't happen. In fact, if you take a more sophisticated point of view, I mean, you're probably wondering why I'm belaboring a trivial example, but from a quantum mechanical point of view, it absolutely could be the case that one ball can roll through the other. It's just the probability is just so small, you know, in all of our lifetimes put together, you'll never see it. In all mankind's lifetimes all put together, right? You wouldn't expect to see it. It's just too tiny. Okay? So that's so what Hume took away from that is that, hey, there is no magic threshold where we can say, oh, no, I've seen the one ball hit the other 1,000,000 times, so therefore I'm 100% confident. His point is you can never be 100% confident based on empirical experience. That's the problem of induction, that you're always making a leap. And they're saying, how do you know that? Well, because I've seen it N times. Okay, well, you've seen it N times, so that has some validity to it, but far from a guarantee. Okay, that's the first issue. Now the next issue is that, let's say we solved the problem of induction, which is not a solvable problem. But let's say we solved it, and now we know that the one billiard ball will, you know, when it hits the other, you know, we know what's going to happen. It's going to happen 100% of the time in the future. Problem of induction solved. We're still screwed
because the world is such that you're never actually in the exact same situation the second time. Right? I mean, is every air molecule in the room doing the same thing it was doing at the time the first billiard ball hit the second? You know, if nothing else, time has advanced, right? Could that matter? Well, physicists think that the laws of physics vary over time. So yeah, it could matter. All right. So that's the problem of feature selection, where in a complex world, like you want to come back to me and say, yeah, but little differences in air molecules and stuff like that is not going to really affect the billiard balls. So we think we kind of know what's important. That's the features that are relevant for a particular problem, right? We wouldn't even try to understand stuff that happens on a battlefield where like everything is happening all at once if we didn't think we had a leg up on this problem. We think we kind of understand what affects what, and that allows us to pull the complicated situation apart and maybe get some insight. Okay, that's the problem of feature selection. Feature selection is extremely hard. Okay, in the world now of neural networks, so we just kind of assume. So this is still, so it's again a little bit of soapbox standing here. You know, we have a track record in AI of solving the problems that we as people are most impressed by. Oh, the computer can do calculus. Wow, therefore it could do everything. And not realizing that, yeah, if the computer can do it, maybe it's not all that hard. And we're impressed by it, but maybe it's not all that hard. Okay? And we're still in a world where people assume that you're going to go and you can train a neural net, you're going to be able to give the neural net the right information to let it solve the problem. You're going to do this for the computer. Okay. To me, as someone who's worked in this field and worked with neural nets their whole career, I think this is a much harder problem than the problem of training the neural net. Okay. This involves deep and wide knowledge of the world, and we don't have AI systems that are great in this domain. Maybe they're on the horizon, maybe not. Let's see. I'm not confident. Okay. Any discussion about this? You know, this is general discussion. It's meant to apply just as much to a person as it applies to a machine. It's just what are the problems that are faced when you go and try to learn from experience in a given situation?
I am aware of both of these from like philosophy classes. In the context of computer science, in the same way that you said, we know that it's theoretically possible for a billiard ball to roll through one billiard ball, but the probability of that happening is so low it is irrelevant. Then in the context of computer science, if you know the reasons that an event would cause another event, and you recognize that the odds of the initiating event happening and not resulting in the consequent event is essentially zero. Why would we care from computer science?
Well,
From a philosophical
keep in mind,
are we all
yeah.
real?
Well,
I don't
yeah,
know.
yeah.
That's fun to talk about. But in terms of like, I'm never gonna be at a billiard table and be like, good.
Click.
Oh,
Well, I'm picking extreme examples though, right? And that's what Hume did too. He picked the examples of two balls rolling into another where you tend to think, well, there's nothing interesting going on here. How could anyone fail to not have certain knowledge of what's going to happen on the billiard table? And his point is that if you really think about it, and you have to admit that you don't know with 100% certainty what happens on the billiard table. Okay, now let's start talking about stuff we care about in modeling and simulation of battlefields, where things are much, much fuzzier, right? And I think it helps you to realize that, okay, even on the billiard table, you have to admit this little, yeah, it's not practically interesting, but that little doubt has to still be there. Now, how about in situations that are more genuinely perplexing and overwhelming, in fact, for people?
I think another part of that too is you have more complex situations, more likely you don't understand some element of it. So it's like the billiard balls in theory, we're like, okay, well, hey, we know what this billiard ball is, we know what this one is. You didn't know that this is just a tennis ball that's painted like a billiard ball, so it reacted completely different than you thought. So the more complex the world gets, the more likely we've completely misunderstood some aspect of it.
Yeah, all set. Other points?
All right. Okay, back to the grindstone here. Let's start focusing down on more practical stuff. Just some terminology here. So machine learning is a pretty broad field. I mean, we're going to get a narrow slice out of it this quarter, but it is a pretty broad field. There definitely are both discrete and continuous, quote unquote, floating point systems. Offline versus online. Okay, we are still in a world, and this is very interesting to me. We are still in a world where almost all learning is done offline. That means in the lab, at the manufacturing facility, not on the battlefield or the work site where things are actually happening. Now, this is kind of for a reason because, machine learning, as if you don't know already, you'll find out it doesn't always do spectacularly. And if you're in the, not in the thick of things, okay, and you can go and do some testing, right? You will realize that, okay, the machine learning seems to have failed. This is not a valid answer. Okay, whereas if you have systems, which we've been able to build these forever, that learn online, constantly, at all moments, then if something bad happens, something bad is going to happen. The behavior is going to become bad, and there's going to be some potential consequences. Okay. Now, there have been examples of online learning. Some of the earliest neural nets that were created were created by Bernie Woodrow at Berkeley, now deceased. He did, you will see in just a few slides, he built a linear neural network. It was essentially a linear model. It was in the context, it was for a very practical purpose. Back in the age of analog telephones, a very real problem was echo, that you'd pick up and you would say something and you'd hear your own voice coming back on you like just a second later. I think we've all experienced how some of us cannot talk at all, can't even talk under that circumstance. I'm one of those people. It drives me absolutely nuts to hear my own voice back in my ear with a slight delay. It's bad. Okay, it's bad. And it can happen very easily in telecommunications where, if you think about it, back in the day, every time you pick up the phone and calling my mother-in-law, the exact same, my phone's the same, her phone's the same, the circuit in between us is always different, right? We used to go through a switchboard, and it was actually human operators are plugging together and creating a circuit between my location and hers, and it was different every time. After the human operators were taken out of the equation, it was still different every time because it was a machine doing the same job, okay? And that meant that the characteristics of the line, including the propensity for echoing, were different every single time. So there was no choice other than to do online learning for this application. It's no good to go in a lab and make an echo suppressor that works on the one line that you're testing on in the lab, but then you bring it out into the world and there's all kinds of other circuits with all different properties, and what are your odds of succeeding? 0. If they could have done that, they would have done that. Okay, so going way back, we've had successful examples of online learning. There is talk now, again, I'm starting to see in the press more and more interest in having systems that actually learn online, despite the obvious dangers and disadvantages of being in an environment now where the learning system can't be easily checked, tested, monitored, what have you. Yeah, I don't know. Something to track. But pretty much all the algorithms that we're going to talk about, like from this point to the end of the course, could be online. There is no reason in principle why you might have to adapt the algorithm somewhat, okay, to be clear. But it could certainly be online if there was demand and if it was really necessary to do that. Yeah, it'd be very interesting to see where this goes in the future.
How does this relate to like the way a lot of LLMs work right now, where they're pre-trained offline, then they're deployed, but they still have access to resources online that they can pull from? Like up-to-date information? Is it some sort of like hybrid situation? Or?
Yeah, that from the broad definition of learning and adaptation that I said, that kind of is a kind of a hybrid situation. If you want to look specifically at the neural net, then you would say, that's definitely offline for the neural net, but for the bigger system, that includes the web queries that the neural net is going to generate and then suck back in to adjust its answer, the bigger system would be adapted. And that's kind of a good way. I think that's a better way to, that's a safer way to do it than have the neural net try to train itself online. Because you'll see some bad things can happen. Okay. Last but not least, we've got supervised versus unsupervised. And what that refers to is, so when you do supervised learning, you are explicitly providing the learning system with the correct answers. And you say, when you see this as an input, you should do that. Okay, when you see this other thing, you should do this other thing. Okay. So a little bit like classroom instruction, here are all the right, here's the material. Here's the things you need to know and what you should do in each case. Okay. Supervising. Okay, well, it isn't always possible to do supervised learning. And in particular, systems that are based on reinforcement learning and things like it are unsupervised, or sometimes people say self-supervised. So these systems learn from experience. They're never told what is the right answer in a particular circumstance. And then there are also hybrid systems. There are systems like the very famous Alpha Star system, which is a reinforcement learner that learned to play StarCraft better than 99.5% of human beings. Okay, so a pretty good system. They started off with supervised learning and then took those networks and did additional unsupervised learning on top of the supervised learning. Yeah. Okay, so example tasks for machine learning, and I think maybe in particular, all of these neural nets can be applied for all of these. So we're going to start off talking about function learning, which is the simplest task that's up there. It can be considered a form of regression, but not the exact same the linear regression that you would learn in operations research, and neither are the algorithms that are used the same as you would learn in OR, unfortunately. Our algorithms are actually simpler, but a lot fewer guarantees. Okay? Function learning is actually at the core of almost everything that's done with neural networks and maybe possibly everything. Okay? So it's really important to understand how you take a neural network and get it to learn a function. If you understand that, then you're just an inch away from understanding how that neural net can be applied to do a whole host of other things. And what other things might you be doing? Stuff like classification. Right, so a famous problem in that domain is you get a spectrum of the return from a sonar ping, and you tell me, is that a rock or is that a cylinder? It might be scary. It could be a mine. Okay, that kind of thing. That's classification. Multiple possibilities. Or I give you an image. Tell me what kind of animal this could be. Dog or cat or kangaroo or giraffe or whatever. Okay, there's classification, but much harder. That's the number of classes. Okay, there's reinforcement learning, which is action selection. Strictly speaking, is action selection in non-adversarial environments. In other words, an environment could be horrible and dangerous and complex, but it's not specifically trying to kill you. It's just dangerous and complex. And then we have gameplay, where you actually have an opponent who's there he doesn't win unless he hurts you. So that's the adversarial. And the algorithms are closely related. And in fact, reinforcement learning is used in such a broad way. Thanks mostly to the popular media, that you could consider, for a point, if you're writing a newspaper article, you could call this reinforcement. But strictly speaking, there's a distinction. And last but not least, predicting what the next word in a paragraph will be, which is kind of the base functionality for large language models. I hope we will talk at least a little bit about that. Yeah. Okay. Okay. So the lab on Friday will be function learning. Okay. So we need to get a little further between now and tomorrow afternoon so that you're set up for that. All right. So let's talk about neural networks. We've all seen a real neuron. This is a real neuron. Neurons are are cells, or normal cells of your body with normal cell parts like a nucleus and a membrane on the outside. However, they're
extremely diverse. Inside any one animal, like a human being, they don't all look like this, but this kind of looks kind of like the stylized image of a neuron that has inspired neural networks in computer science. So that's why it gets to be up there. And yeah, they're not glowing green inside your head. This one's been injected with that. So don't worry. If yours are glowing green, you've been in some bad environment. Seek medical attention. All right. So here's a cartoon. Okay, just to kind of show the kind of similar thing to what you just seen. It's oriented a little differently. So tilt it up this way, it looks like the picture. Okay, so a neuron is from one perspective, just a cell, but from another perspective is an information processing device, the input end, and this is the output end. It's not always so cut and dry as this, but that's why we like this picture. It's all clear. Sometimes the inputs and the outputs are kind of mixed together in a complex sort of way. Okay, so you got your nucleus of your cell here, and then you have these little processes, these little extensions of the cell body. These are called dendrites. Okay, and out in the very tips, these dendrites are generally, so most neurons talk to other neurons. Only a few lucky neural cells get actual information from the outside. The rest are just kind of discussing the same information one with another. Okay, so mostly they're getting information from the bouton or the feet of another neuron. Okay, and each adding some little increment to the discussion that hopefully results in some good action. Okay. These longer neurons, the ones that really run for a while, including the ones from sensory cells and running from your feet up to your brain, right? They would not be able to do their job unless they were insulated, much like metal wires. If there was no insulation, they will just short circuit in one another. And in fact, as a result, this causes a lot of like Alzheimer's and so forth, as I understand it. A lot of it comes from degeneration. So, okay, enough biology. Okay, this is also a neuron, a mathy neuron. Okay, here's the input end over here, and here's the output end over here. Now what's going to come in is, instead of an electrical impulse of a certain voltage, what's going to come in is a number, a floating point number. And here we have n inputs, so here are those n floating point numbers, I1 to In. Okay, and so it's going to do some computation. What specifically does it do? Okay, you will be amazed to see how simple each individual neuron is. And a neural network is just a whole bunch of these little guys. Okay, what does it do? It's doing multiplication. So it has some weights here, one weight per input, so it multiplies the value of its weight. Consider this also to be a floating point number. So this is a math model now. One polling point times the other one. So now the signal on this line here is I1 times W1 and etc. the whole way down. Okay, and if you squint at that, you can say, oh, that's like halfway to producing a dot product between two vectors, right? You just got to multiply the corresponding entries, right? And then what do you do next? You add them all up. Oh, here's sigma for sum. We're going to add them all up. Okay, so it's an inner product between the weights and the inputs. And then we're going to add a bias, add one extra number in. Okay, and we're almost done. If it's a linear neuron like Bernie Woodrow, we would be done. Okay, but in fact, linear neurons can only do so much. Okay, they are too limited for, we would never have all the advances that we've had in neural networks if you only had linear neurons. So in fact, you take that output and pass it through some nonlinear function. Which one is a matter of some debate, and it's different in different contexts. Okay, but there's kind of a lucky winner these days that I'll tell you. So it's one that most people use these days, very, very simple as well.
It's a naive function, like 0 and 1.
So that would be like an extreme example. Yeah, well, this is the time you're going to get it. All right. So wrap that all together. And I'm about out of time, so I'll stop here. But this is a neuron for us. This equation. Okay, it gives you an output as a function of n inputs, and how does it produce it? Takes the inputs, multiplies by the weights. sums them up, adds to B, passes it through this F function, whatever it can be. And this is the traditional shape, kind of an S shape or sigmoidal shape, is what it used to be called. And that'll do for today. Any questions? All right, cool. So tomorrow we will do an amazing amount to get ready for Friday.
1400 tomorrow, right? On the other side.